All right, so we've been talking about waves and resonances and standing waves and things like that. And I know there's a bit of a leap from knowing the basics of a wave traveling through air and compression and rarefaction and all of that to really getting what's going on with standing waves. And especially when we get into perturbation theory, we can calculate the basic resonances, but why do these resonances go up in this situation or down in that situation and so on. So I found some really, what I think are some really helpful illustrations made by other people that I'm going to walk through and sort of hopefully connect these dots in a visual way. I've got some metaphors and ways to visualize and sort of think about it as a story that might help if the basic physics descriptions aren't quite doing it for you. Okay, so we know about waves, and this first illustration, this first illustration is from this website. I'll put the links to all these websites in the description of this video. And here's the animation that we're after. Now this is a wave that's traveling towards this surface. It's going to reflect off this surface. It's traveling. I'm going to hit resume here. You see it's traveling. We see the pressure increasing and decreasing. And as it hits there and gets reflected back, there's this sort of inverse wave that gets created in the reflection. And I'm going to pause that here. So the red is the incoming wave and the blue is the outgoing wave. And you notice as they overlap, this black, which is the actual pressure at any given point, instead of just being the pressure of the one wave, becomes the sum of the two waves, one going to our left and one going to our right. And that sum, if they're both negative, it'll add up to a more negative number. If one's positive and negative, and they can balance each other out, or not quite, and really positive, and so on. So as we continue, as we see these waves, they have exactly the same frequency, exactly the same amplitude, and so we see that they interfere in this very particular way, where the sum, as the waves are moving the way we're used to, the sum of those waves, the actual pressure at any given point, becomes this standing wave, where we have a node, we have very little particle movement at this surface here. Then we have an antinode where it moves back and forth, like we get really high highs and really low lows, and we get nodes and so on along the way. So the point of this illustration, I'm just going to come out of that for now. The point of this illustration is just to show you how a wave and its reflection can interfere with each other to create a standing wave, a wave where those fluctuations in pressure, instead of moving through space or appearing to move through space, as we know from how waves work, when we have this really interesting interference pattern, in fact, we still have a wave going that way and a wave going that way. But in terms of the measurement, what's happening to the pressure is this standing wave. It's like it's fluctuating back and forth in place. You zoom out enough, you'll see the wave coming in and the wave going out. It's not going to overlap into infinity, but in this localized space, you have this standing wave. And that's what happens in enclosed spaces, tubes, vocal tracts, musical instruments, things like that. Okay, so that's enough to get us to, yeah, we've got these waves that wobble back and forth. Now I'm going to go to another website. Now this is a website that is hosted, it's by Dan Russell. He's a physicist working in Penn State University in the United States. And this is a physics program. And this is just about standing waves. So we're going to start with this illustration here, which I'll zoom in on. So here is, we've established that these standing waves happen. Okay, if you want to go back to that illustration and really get it into your brain how that's working, then by all means. But now I'm working on the assumption that illustration worked to get us there. So now we have these standing waves, and we can now give a static representation of a standing wave instead of having to see it wobble back and forth as we do here. We see the black wave wobbling back and forth. We can just take the top and the bottom extremes, and we get something like this, where at the top extreme it's there, at the bottom extreme it's there. Okay, and we have different standing waves. These are different resonances. Why do we have different resonances? I'm so glad you asked. This is covered in the materials, but it's worth getting back into it, and I am going to introduce and really get every ounce of every modicum of value out of this metaphor that I can. We're going to imagine that this is a hallway and people are moving back and forth. Now, in a standing wave, if this is a hallway and it's open at this end and closed at that end, people are moving back and forth. If you're leaning against this wall, the closed wall at this end, you really don't have a lot of space to move back and forth. Remember, it's a longitudinal wave, so the actual particle movement is this way. And you don't really have a lot of space to move this way, so there's not going to be a lot of movement. These ones on the left are displacement of air, so not a lot of movement. But if you're at the other end of the hallway where the doors are wide open, you can move back and forth all you want. And so you have a lot of movement back and forth. Now, the waves, the frequencies and wavelengths that fit well, that resonate in a tube, are those that obey these particular things. This is a wave, this first one we see here, is a wave that fits well because when the standing wave is set up, the particles at this end don't want to move a lot, and the particles at this end do want to move a lot, and they can. They don't want to move a lot, and they can't. If you had if you had a wave where the particles wanted to move a lot at both ends, or they wanted to not move a lot at both ends, that wouldn't quite fit the vibe of that hallway with the closed end here and the open end there, right? So this is definitely me going beyond the strict physics interpretation of resonance and trying to come up with a visualization that helps from remembering, right? That hallway vibe. Any standing wave where the particles don't have to move a lot at the closed end and they can move all they want at the open end, that's going to be a good resonance. It's going to be a wavelength that really works well in that hallway, in that tube. So we see this first one, there's a node there, meaning minimum change, and an antinode there in terms of particle movement. And that fits well. But this other one, this is also a wave that has a displacement node there and a displacement antinode there. It happens to have another node and another antinode in the middle. That's fine. As long as this end and this end are behaving well, that wave is welcome to do whatever else it wants. We can have a third node and antinode as long as those ends line up. So this is the essential idea of how we get multiple resonances in a tube, is that by adding extra bits until we have that closure at the one end and the opening at the other end, we get that happiness, that consilience. The wave fits well in that space as a standing wave. Okay. So we can get these multiple resonances. And you'll notice that this diagram talks about harmonics. This is harmonics in a different sense than what we're generally talking about in terms of speech. So you can ignore that. This is the first, second, and third resonances. This website talks about the first, second, and third mode somewhere. Yes. But we'll talk about resonances, which are in turn going to become formants. The other thing about this particular graph, we see the things on the right, which are almost exactly like the things on the left, except here we have a node at the open end and an antinode at the closed end. Remember, node and antinode are mathematical terms. Node means not much change, antinode means maximum change. And both of these things are true. Because they're depicting different things. The one on the left is depicting displacement. This is movement. You can't move a lot when you're up against the wall. You can move all you want when you're right by the door. This one represents pressure. So pressure, if you imagine that you're up against the wall and people are moving, well, they don't have to move a lot and you're suddenly getting really squished. They don't have to move away a lot and suddenly, you've got space. Like you could move towards them, but then you've got gap on that space. Like your pressure is increasing and decreasing dramatically. But the person at the open end, at the end of the hallway with the wide open doors, well, if someone moves towards you, you just move out of the way. You got all the space in the world there. If someone moves away, you can move closer. You got lots of movement there. So that is why on the pressure representation we have a node at the open end and an antinode at the closed end of the hallway or the tube. And then we can fit in, it's the same wavelengths, we're just in the same waves, we're just depicting, instead of particle movement, we're depicting pressure. So pressure is changing where particles aren't moving much, and where particles are moving a lot, the pressure actually isn't changing in this standing wave. Okay, so that is to say those graphs on the right and the graphs on the left are depicting the same waves, they're just representing different aspects of the standing wave. And this is where we're going to get into the next illustration here, and this is turning back to animations again. You saw an example of this already on that website. I'm going to make this as big as I can. So here at the bottom we have something like that first graph that we were looking at. I'm just going to set that going, where the wave is swinging back and forth. This isn't actually a resonance, this is just a interference from a reflection, but it's the same idea. So we see that, here, swinging back and forth. This is just a first resonance. Here we see the same thing happening, but for pressure. So that's why you have more change at the closed end and less change at the open end. And up top, I really like this illustration. It's got a bunch of particles, and we're seeing them move back and forth. Now, of course, air particles are minute, so you can think of these as really, really, really magnified particles so that we can see them. And it's a subset. There would be billions of particles, in fact. But anyway, and we see at this end, the particles are barely moving at all. They're right up against the wall. And this end, they're moving a whole lot. But here we see they're basically the same distance apart all throughout, because the particles next to them are moving fairly lot as well. So that's why the pressure isn't changing. But here, any movement has to be basically a change in pressure because you're not getting out of the way. So that animation there is meant to illustrate that trade-off or that opposition between movement, particle movement or particle displacement, and pressure. Okay. And now we can see the same. We have illustrations. You can go to the website. It has, I think, 4 different illustrations. This is just the second resonance. Again, not a lot of movement at this end where it's closed, and a lot of pressure change. Whole bunch of movement at this end, but the particles are staying about the same distance, so a lot of movement, not much pressure change. And then here we have an intermediate movement node and pressure and movement antinode, or pressure antinode and a movement node here in between. But as long as the ends are behaving the way we want them to, we can do other things in the middle. Okay, so we've got people moving around in the hallway. Now, the last main concept that we're covering in this section is perturbation theory. What happens if the tube is constricted or widened at a particular point? What happens to those resonances? Now, for a uniform tube, we can calculate the frequency of those resonances based on the wavelength, how much of the wave is fitting in the tube. And that material I'm not going to go over. That's some math. You can kind of infer some of it from these depictions, but we'll set that aside. When it comes to perturbations, you're narrowing the tube or widening the tube at a particular point. How does that affect resonances? And here's where I like to go back to that first resonance and the people at the closed end of the hallway and the people at the open end of the hallway. Now imagine you're someone at the open end of the hallway, you're moving back and forth. It's really easy to move through the doorways because they're wide open. Now imagine it's a double door. You have the double doors open and one of the doors gets closed. Well, now there's much less space to get through. And so if me and my buddies are trying to get through, well, we might have to sort of go single file through the door or 2 at a time or something. We can't get through as quickly. It's slowing down that movement, and that slows down the back and forth, the frequency of resonance. We want a wave that doesn't resonate as quickly so that we can get back and forth through this now narrower opening. So when we narrow the tube at the open end, it lowers the frequency of the resonance. Right? Go back to that. Here's the open. That, if we were to narrow it here, that resonance would become a little bit lower frequency. On the other hand, if you're at the closed end, you're already getting squished and then stretched and squished and then stretched. You're getting a lot of pressure variation. Now imagine that that hallway was narrowed. They moved the walls in by a couple of feet. Well, now, not only can you not move out of the way back and forth along the length of the hallway, but all of these particles are squished into a smaller space. So as soon as someone new comes, well, if someone new comes into that space, into that end of the hallway, our pressure is going to go up much quicker because we have less space to fit extra people in. And similarly, if people leave, well, there's less space, so one person leaving leaves a bigger proportional gap in the space. I'm stretching the metaphor a little bit here, but you can imagine pressure is going to build up and drop more abruptly if we narrow it at that closed end. And so narrowing there tends to increase the resonant frequency. We want a wave that vibrates a bit more quickly to fit. Yeah, and we see that's an opposition where when you're at the open end, you have the opposite effect than when you're at the closed end. Okay, now what else do I want to say about this? Well, that's basically all the principles that you need. If you then move to a higher resonance where there's, see, we have a movement node at the closed end, we also have a movement node somewhere in the middle. Well, all we have to do is think that part of the hallway for that particular resonance is kind of acting like the closed end. If you're a particle hanging out there, you just can't move around very much. And so you're going to be more affected by pressure differences, and you're not going to be able to move around very much. And so narrowing or widening there is going to do the same thing as if you were narrowing or widening at the closed end. And similarly, when you look at the extra, the extra displacement antinode, you see the particles, the people in the hallway are able to move around fairly freely there, just like at the open end. So narrowing and widening there is going to have a similar effect to narrowing or widening at the open end. So narrowing moves the frequency in one direction, widening just does the opposite, right? You close that door at the open end, that lowers the resonance frequency, and in fact, all resonances have a displacement antinode there. They have that free movement property at that end. So all resonances will have a lower frequency if you close one of the doors, if you narrow the tube at the open end. And all frequencies have a displacement node at the closed end. That's where the particles aren't moving much. So all frequencies will, all resonances will rise in frequency if you narrow the tube at the closed end. And vice versa. If you widen at the closed end, that will lower the frequency. If you widen at the open end, that will raise the frequencies. And any other place along the way that is like the open end will react like the open end would. Any other place along the way that is like the closed end will react like the closed end would. I'm trying to phrase this mainly in terms of the closed end, the open end, and what's happening there, because that connects to our story. And then if we really have to, we can nail down, okay, this is a pressure node because the pressure isn't changing much, or this is a displacement node because the particles aren't moving very much, or it's an antinode because of the opposite, right? You can sort of make that connection along the way, but you need to remember, as we've seen in all of these depictions, that a displacement node is a pressure antinode. A displacement antinode is a pressure node. Anywhere in any of our resonances, even when we get to the higher ones, antinode here is a node here is an antinode here, right? So people in a hallway trying to get around, that is how I always remember this. I am not a physicist. I know this is a physics module in a somewhat math-heavy course, but this is really almost completely all the physics that I know. But there are stories we can tell ourselves to kind of remember how these things go together so that we can connect these concepts to eventually to what's happening in the vocal tract and how we make different sounds. Okay, I hope that helps. I know this is a complex topic, and it's always I find it's always valuable to have different ways of thinking about something. If one of them hits, if one of them connects and helps you get through these concepts, then that's great. Okay, thanks for watching.